So for 3 years, from 2012, I got funding from KMA. It's about the wintertime seasonal prediction. So since 2000, maybe when I analyze data set after mid-1919, cryosphere is changing so much after mid-1990. When I apply changing point analysis, it's a kind of trend analysis, and then when there is a huge change occurs, we can detect using the changing point analysis. So with my analysis, it's 1998. Before that, the cryosphere was a little bit calm and not cold, not warm. But after that time, cryosphere becomes very warm. So we specifically refer that phenomena as Arctic amplification. So sea ice melting a lot, and then temperature increases a lot. So that means cryospheric condition is changing a lot in this decade. So in this century. So it's very important question to examine what is the impact of sea ice and snow cover on seasonal predictability. So I mean the cryospheric elements consist of sea ice and snow cover. So both are changing a lot in this century. So there may be an increase of potential predictability in the seasonal prediction. So I got funding from KMA, and then this is the last year, 2014. It's a 3-year project. So maybe soon this project is ended, and then I have to write down final report. Okay. And also, every year I attend expert meeting on seasonal prediction. During wintertime, APCC and I become competitor, good competitor in the wintertime prediction. Maybe I remember this year APCC predicted a little bit warm winter. I predicted normal winter. And last year, I remember APCC's score is very good. They predicted a warm winter, and actually it was very warm winter. But 2 years ago, I remember APCC predicted warm, and I predicted very cold. I was winner. But when you see some history of this competition, then you can find one thing. APCC predicts always warm. I predict always cold. It depends on nature. Winner depends on nature. So it's far away to go. Anyway, yeah. So, but this competition is now ended because my project is done. I will not give my operational prediction anymore. So it's a kind of joking. Thanks for laughing. Anyway, so now I start my talk. This is a little bit historical background of my talk. Okay. So nowadays, sea ice and snow cover are becoming popular issue in the seasonal prediction. And the main argument is that Arctic sea ice loss and snow cover is changing tropospheric jet stream variability in the upper level. So this means that when sea ice and snow cover distribution is different with normal year, then tropospheric jet, especially polar jet stream, maybe it's a polar jet stream or it's meandering due to this kind of cryospheric condition. So jet stream, basically jet stream responds to this condition. And also in some part of middle latitude, like Eurasian continent and North America, so they suffer cold winters. Nowadays, this topic is very popular, and more than 100 papers, maybe more than 300 papers, I think. So these papers are reviewed in this paper, VIMA. So Survey of Geophysics. He was very precise person, and then examined in detail, and then categorized every mechanism. So this is very good for comprehensive review. But there are different ideas, especially for these big guys. Wallace and Isaac Heard and Thompson, David Thompson and Travers and John Walsh. These people are all famous. They don't like this idea, I think. Yeah, they don't like. Their main argument is that something like that, it can be, but they have not confirmed the hypothesis. And we do not view the theoretical argument underlying it as compelling. So in summary, so less evidence, not sufficient evidence they are arguing. So actually, nowadays, this topic is under hot debate. Last year, one paper is published insisting that this mechanism is very plausible, and there is some schematics about that. Actually, this paper is talking about factors influencing this kind of jet stream and planetary waves, storm tracks, and polar vortex. And these factors are very potentially important to change this middle latitude element. And storm track changes and jet stream changes can cause some coldness in the Eurasian continent. Some northern hemisphere middle latitude weather is tightly linked to this dynamical element. And these are summer and early fall Arctic sea ice loss, and fall Eurasian snow cover, and late fall and winter Arctic sea ice loss. So they say these factors are all related with Arctic amplification and very efficient for changing these elements, dynamical middle latitude elements. And then some region suffers cold extremes. Some papers insist that these elements cause not only cold extreme, but also hot extreme. So heat waves and some droughts. Yeah. So because this is related with the planetary wave and some blocking low frequency variability, so this kind of changes can cause some regionally sustained variability. So recently, I published a paper about the linkage between sea ice loss and stratospheric polar vortex. Already, this paper reviewed my paper, and so my mechanism is working in this route. Late fall and winter Arctic sea ice loss and Arctic amplification, it causes planetary waves change in the troposphere. And it propagates upward into the stratosphere. It can change polar vortex. And then the polar vortex is tightly linked with the Arctic oscillation. It's because we call another word of polar vortex is northern annular mode. And also surface manifestation of northern annular mode is Arctic oscillation. So this also linked with these elements. So So this is another evidence that sea ice loss is linked with the tropospheric variability. So I briefly introduce my argument. So I composite Barents-Karasi sea ice loss because I think I presented this topic several times here. So I would like to briefly introduce. So I gathered years with the low sea ice over this sector. And then I conducted composite analysis, extracting these years and averaging these years, what happens. So this is the result. So this is the observation. For substrate temperature, we have a warm Arctic. For less sea ice over here, we clearly see very warm Arctic here and very cold over here. It's a well-known warm Arctic, cold continent feature. But as you see, this is a composite analysis, but members are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just 11. So even though this feature is very clear and very kind of auspicious, something, very clear, but members are very small. So statistical tests, if we conduct a statistical test, then very difficult to exceed 95% statistical significance evidence. I believe most of this is related with this debate. Actually, sea ice cryosphere changes are recent phenomena. So whatever we do statistically, it's very difficult to prove. So they do not believe their analysis results. That's the reason. So I did modeling analysis. So I used a Chem5. We used the Chem5 model, and we prepared 2 sets of experiments. One is control, and the other is sea ice reduced run. Sea ice reduced run, perturbed run is consists of the composite seasonal cycle of sea ice and SST from these years. But we just prescribed only for the Arctic Ocean. So we just prescribed the boundary condition over this region, and outside of Arctic, boundary condition is prescribed with the climatological condition. So no forcing, just Arctic forcing is applied. And then, so perturbed run minus control run defines some response. So both control run and perturbed run were conducted with the 40 ensemble members by slightly modified initial condition. So response is then defined as ensemble mean difference of the 2 runs. Okay. So these are results. So using Chem5 model, and also we prepared Chem3 models, these 2 models. And then even though the signal becomes a little bit weak, this warm Arctic and cold continent pattern is well captured by the model. So this means that even though members, composite members are small, 11 members, model verifies that this phenomena is qualitatively true. It's originated by sea ice loss. Okay. So this is upper level, same figure but upper level, 500 hectopascal geopotential height anomaly. So this is a composite for using 11 years. You can see that well-defined stationary wave emanating from the Arctic, high and low pressure. Here this is a Korean peninsula, and then the synoptic meteorology scientists well know that when there is a large-scale low pressure over Siberian region here, then there is a cold advection in this region. So this is well-known synoptic upper-level cyclone At the coastal, we call it coastal trough. This kind of pattern is a very good condition for cold winters. And this is Chem 5 result and Chem 3 result. So comparing these patterns, can see there's some difference, but qualitatively we have some similar features here. Chem 3 is better in the upper level response here. Also, this is very interesting result. So this is a annular mode response I compared. This is a 11-year composite. Whenever sea ice becomes less, I plotted a polar cap index. It's a daily polar cap index, time and height cross-section. So from November 1st to March, end of March, I plotted polar cap index. So positive values means positive geopotential, average positive geopotential height in the Arctic. So negative annular mode. So you can see that this figure shows when there is a less sea ice in the Barents Sea, we have a so-called negative AO dominating winter. And also in the midwinter, we have a stratosphere connection here. So Mather, interestingly, captured this picture also. So with this figure, I confirmed that there is some connection, sea ice and stratosphere linkage. So this is a result. But today, I would like to talk about predictability. So you can see that this is a temperature response. So this is a little bit different run with the previous modern run, but qualitatively similar. So you can see that warm Arctic and cold, there is a cold continent, but it's a much weaker response here. But so this is internal variability, actually. For early winter, this is a surface at temperature. So this is you can think this response as a sea ice response, but this is just November, December average, the internal variability, just standard deviation for long 40 ensemble members. So we have a 40 November, December average surface air temperature, and we just calculate standard deviation. Then we get this map. So this ratio is forced response divided by internal variability. So this feature shows if this is over than 1, then forced response is bigger than internal variability. But it's less than 1. So this means that forced response, sea ice reduced forced response usually less than internal variability, random variability year by year. So it's very subtle. But at the surface, we have it's 0.775, so it's comparable. But in the upper level response here, this is 500 hectopascal. So the ratio is below 0.5. So it's very small. Circulation response is very subtle, and it's difficult to pick up forced response in the pick up forced response in the random fluctuation of every year fluctuation. So we need to be very careful. So this means that high latitude region, internal variability is very high. So we need to be very careful about interpreting the cryospheric signal. Okay? So this is another paper, the Mori et al. So this paper is very similar to my study because this paper also looked at the sea ice response, and then actually configuration is almost same. So they picked up years with less sea ice in the Barents Sea and see the response. So this is a Barents Sea, so warm Arctic and cold continent pattern. This is observation, and this is model. This is a very similar result with my result. But this, I like this paper because this paper is much more rigorous than my one. So they calculated uncertainty of response. Okay. So what they did was they examined this box average core temperature, and then depending on the ensemble member size, the ensemble spread becomes different. So this is ensemble mean response, and they basically examine the spread. So, and this is the figure. So when ensemble member is just a number 10, the box average, the subset temperature is below 0, but spread is quite big. So we cannot certain that warm Arctic cold continent in this case because error bar exceeds 0 point. So very uncertain. But when we increase ensemble member, the error bar becomes small, but ensemble mean stays there. So after maybe 70 members, we can certain that this response or sea ice reduction in Barents Kara Sea actually causes cold winter. We can confirm that this argument with the modeling simulation. But more than 70 ensemble members, it's huge members, isn't it? So this indicates that it's very difficult with just laboratory experiments. We can study. It's very difficult to study Arctic and mid-latitude connection due to the notorious internal variability. We have to be very careful. This is my first message about this in this talk. So with this argument, it's my private opinion. So cryospheric impact, especially sea ice impact, is robust and detectable, but internal variability is so high. So more than at least 50 ensemble members in experiments are needed to depict the forced response. Okay. With this background, so I would like to introduce my seasonal prediction effort here. So our team developed a seasonal prediction system based on physical variables in the cryosphere. Okay. So I'm sorry for Korean. Okay. So during 3 years, I proposed a project goal, dynamic understanding of cryospheric impact on mid-latitude subseasonal and seasonal variability, and development of statistical and dynamical prediction system based on the above understanding. And ultimate goal is improving seasonal prediction scale. This is a simple goal of our project. Now our team consists of 6 teams are. We constructed 6 teams. So Professor Seok-Son examined the stratospheric natural variability, and in Jeju University, he examined future prediction of East Asia winter monsoon. And these are core of our dynamic monsoon team. We need a sea ice prediction model, and we need a snow initialization model to have a dynamic forecast, wintertime dynamic forecast. So Professor Yong-Sang Che examined a sea ice prediction model. Jeonnam University Professor Ji-Hoon Jung implemented snow initialization, especially over Eurasian land cover region. And we have a statistical prediction group. SNU, Gyu-Ho-Rim did that. Okay, this is a kind of schematics of our dynamic system. So a little bit complicated, but it's not that much difficult. So this is a kind of we use AGCM only. We don't use CGCM. So this is a very important point. So I will explain a little bit more later. Anyway, we use AGCM framework. So we need a boundary condition and initial condition. So as a boundary condition, we use Hadley SST and OI SST. And we need a CI's prediction boundary condition. So usually we run this model from November 1st to the end of winter, end of March. So during that period, we should have a boundary condition prescribed. But how can we know the boundary condition? It's very difficult. So we have some simple linear relaxation method here. And then during the project, we realized that SST and CI's relationship is very important when we use this framework. Suppose we prescribe some CI's boundary condition. Then how can you know SST consistent with the CI's? It's very important because when SST is, we just use climatological SST at the time, then surface heat flux is very small. So when reduced CI's have a consistent SST value, then the heat flux becomes very large. So that kind of variability is very important in the model response. We realized that. So I will briefly introduce this component also. And also, this is a usual initial condition. We prepare ensemble members using NSEP FNL analysis. And this part is we use JCDAS. Recently, we replaced this using JRA Gogo. They have a snow depth data, observed snow depths. And then we use that data in the snow initialization. And then we run the model using this boundary condition and initial condition and seasonal prediction system.
What about the SST in the tropics?
Oh, that's a good question. Actually, we prescribe the climatological value. So actually, this is a semi-operational, not operational, because the goal is we just try to evaluate in this period the impact of how much snow cover and sea ice is important in the seasonal prediction. So that's primary goal. So we just prescribe climatological value in the tropics. Okay. So I will talk briefly about sea ice boundary condition. So as I mentioned, we do not use CGCM, but most of these days, most of seasonal prediction uses CGCM. So why we use AGCM? It's just because cryospheric elements in this coupled CGCM is very, very bad. Very, very bad. That's the only reason. So this is the example. So this is CFS model, and this is a Hadley, this is sea ice extent in the Hadley data, wintertime sea ice extent, black curve. And you can see that this is a read, 0 read and 1 month read, 3 months read, 5 months read, 7 months read, 9 months read. You see that 0 months read, of course, model is very good, because this model initializes sea ice product. But just 1 month read, it diverges from the real sea ice value. So bias is so huge. So and just 1 month, so sea ice in the coupled model diverge from the observed sea ice. No matter how we make effort, at the initial time, model is very, very close to the sea ice, but just 1 month, it diverges a lot. So in this case, we cannot use this CGCM so as a prediction, plausible seasonal prediction system. So this is the reason why we use AGCM model. Okay. Okay. This is also one of our member, Professor Ji-Hoon Jung, made some statistical sea ice model. and then compared it using, this is based on SEOF technique. He developed a statistical sea ice model. You can see that it's much better compared to dynamic sea ice model. But we cannot be free with the argument about overfitting problem, something like that. But some promising, very promising. But when we submit this paper, we first rejected. Anyway, it's a different story. When you join the lunch, then I will tell you about this. Anyway. So simply, we are trying to implement statistical sea ice model using SEOF now, but we just tested very simple method in this case. So we need a boundary condition. So we exploited that the sea ice has a very strong seasonal cycle, usually. So this is sea ice extent. So this is observed sea ice extent for climatological sea ice, total sea ice extent here. So September, October, January. So September, sea ice extent is usually minimum at the September, and then it increases when we winter progress. So the extent becomes larger here. So suppose usually we start model using November 1st here. So we need the boundary condition in this period. So suppose we have 1 year, we have a sea ice extent in October is here. Then we implemented that the linear relaxation. It follows the climatological curve. At every grid point in the Arctic, the sea ice becomes larger as winter goes on. This is just a very simple relaxation, but the signal is damped. Just the amplitude becomes smaller and smaller. And finally, when it becomes March, it is just a value of a climatological condition. Because we just start here, so I think this is a very reasonable assumption. Okay? And so we prepare this sea ice prediction model. And we published one paper about the relationship between SST and sea ice. So when we try to use this sea ice implementation, we also need to know the SST at the grid point, in the Arctic grid point, consistent with this sea ice value. So how can you know? So we just used a simple polynomial fitting about sea ice and SST. The historical data, we plotted relationship between sea ice and SST, and we have a nice second order polynomial line here. So this is a very simple curve actually. Suppose sea ice concentration at one grid point, sea ice concentration is 40%, then we have a 1 degree of SST at that grid point in this formula. So why we use this formula is that previous studies just used the sea ice anomaly and then used climatological SST value. Then it's usually much colder. Then atmospheric response is much smaller. So this is not good. So that's why most of AGCM model failed to capture reasonable sea ice impact on the atmosphere. So SST is very important because important factor is the heat flux from the ocean to atmosphere. So energy component is mostly related with the SST value. Sensible heat is a difference between atmosphere value and ocean value. So SST is very important in the Arctic. But unfortunately, SST in the Arctic is a very uncertain value in the observation. So it's very unfortunate. Okay. Now next, it's a snow initialization part. This part. So we just get observation data, snow depth observation. Snow depth observation is also very, very uncertain. So it's a kind of another uncertainty comes from the observation. But anyway, we just use snow depths. And then we use Canadian Meteorological Center daily snow analysis, and it's a 24 kilometer by 24 kilometer. But this is just for hindcast because they don't provide analysis data. For analysis data, recently we use JRA Gogo. They provide almost analysis data. I mean, so just 7 days before, 7 days lag exists. So we can use for seasonal prediction. But we cannot use this snow depth data directly into our model because, as you see, sea ice in the full coupled model, sea ice model is very bad. So there is a huge bias. Same with that, snow also there is a huge bias. So we cannot use directly. So we simply use some trick. It's a scaling. Just we scaled this is standard deviation of observed snow depths, and then this is a model snow depths. So normalization, we just take normalized information from the snow depths. So to prevent model drift, okay? And then I don't have much time to explain detail, but in the CAM model, we have some snow layer. So suppose we have observed 9 centimeter of snow depth anomaly, then we have a rule to ascribe some values in each snow grid. Yeah. So there is a rule. Okay. So we implemented this. Also, to prevent inconsistency between atmosphere and land surface, so we used some buffer zone. I mean, so suppose this is a forecast starts from here, then for 1 month we notch atmosphere forcing for 1 month, daily atmosphere forcing here, and then the land surface is smoothly adjust with this kind of forcing. So we implemented this. We hope that this method improves skill quite a lot, but result is not so quite a lot. Anyway, we tested this methodology. Okay. So this is the result. So solid line is without adjustment. Dashed line is without adjustment. Solid line is with adjustment. So you can see that this is a sawtooth pattern is a kind of daily atmosphere forcing, and land surface is adjusting with that kind of forcing. So difference is like this. Okay. So this is I would like to skip this slide, and I would like to show you some simple hindcast results. So with this sea ice boundary condition implementation and snow depth initialization, we tested our model seasonal prediction predictability using from 1999 to 2012. Okay, 13 members we tested. So this is the simple result. Actually, we are preparing this paper, so it's not finished work. So I didn't prepare the statistics, more elegant statistics. So you see that this is a Siberian temperature, and this is observed Siberian temperature, and this is a model Siberian temperature, and the solid dot is a Siberian temperature, and open circle is Asian temperature, and cross is Arctic temperature. So you can see that in the Arctic region, the correlation is very high. But in the Siberian region, the correlation is a little bit spread. But Asian region, the spread is quite reasonable. So this is a real predictability. We calculated R square value, then R star value, and this is a this information tells us that when this is bigger, then its real predictability is good, and blue is bad. So you can see that predictable region is, fortunately, Korean is quite influential region. So this information, so comparing these two figures, Arctic region is quite predictable and Asia region is quite good, but Siberian region average, it's not good, it's quite spread. So this hindcast results tells us that our technique is gives some useful information about seasonal prediction. Okay, so we are preparing this paper, okay, in the Korean local journal. This is the final topic. So I would like to emphasize physics uncertainty remained still. So recently I'm working with I worked with Eugene. Yeah, he wrote a paper with me together and Professor Yong-Sang Choi, which it's about sensitivity. This paper is a little bit different with that topic, but the point is that this is a Arctic low cloud representation in the model. It's a huge problem. So in Bavlus and Wallis' paper, they informed us that model has a very big problem in simulating this kind of seasonal cycle of Arctic low cloud. So dotted line is observed seasonal cycle of low cloud in the Arctic. As January and December, you can see the clear seasonal cycle in the low cloud. So less cloud in the wintertime, large cloud in the summertime. But CCSM3 shows no seasonal cycle, always too much low cloud. But this is not just the problem of CCSM3. It's a well-known problem of CMIP3 models. It's an old paper, actually. I don't know current model, how much they updated, but so usually too much cloud in the Arctic is problem. So too much cloud sometimes hinders sea ice response, because usually when sea ice reduces, large heat flux comes out. But when in the sky there is already cloud, very cloud, then heat flux does not have a good ability to produce. There is already large cloud. Then even though less sea ice tries to make a cloud, but already large cloud there, then radiative forcing increase is very small. So that means impact of my English is become more clumsy and clumsy because I'm a little bit tired. So the impact of that kind of a phenomena is becoming less in the radiative forcing sense. So climatological condition of low cloud distribution is very important in the sea ice and mid-latitude response circulation linkage. So they devised a very simple method to reduce this cloud. So after, this is usually low cloud is calculated using the relative humidity. And the F is function of relative humidity. Many climate model uses this formula to calculate low level cloud. So when relative humidity is large, its cloud is large. But just simply multiplied one factor depending on specific humidity. And then this formula reduces cloud a lot when temperature is very cold. So with this formula, they obtained this condition, this simulation. So very similar to observation. So this is a freeze-dry modification. So we applied this formula, even though this is very clumsy, and actually many people attacked this paper because this paper is not physically plausible. Just get rid of moisture, so energy conservation is destroyed, something like that. But anyway, it's more realistic. So I applied this formula. And then sensitivity is huge. So this is a freeze dry on, this is a off, without freeze dry. So that means I applied this formula to off simulation, this formula on simulation. Other conditions are perfectly same. So let's see the response. The results are very different. So, oh, I'm very sorry, the swapped. This is on, this is off. So when low cloud bias is eliminated, then we get nice feature, warm Arctic, cold continent structure when sea ice reduces. But with this on, off, Barbaros off condition, so warm Arctic, cold continent feature becomes very weak. So warm Arctic, warm continent actually. I think this is because upper level response is different. So with Barbaros on, there is a very clear upper level response. That means low cloud hits upper level a lot, then circulation response occurs in the Arctic, and then this is a kind of stationary wave interact with the polar jet stream, and there is some wavy pattern. But this wave pattern is very weak in this case. And also polar cap response. So there is a very nice sea ice stratosphere connection in this case, but in this case, it's very weak. So what I'm trying to tell you is that I don't insist that this is true, but sensitivity. With just this simple modification, low-level cloud, low-level modification, dynamic response becomes huge different. So, okay. Now, I would like to conclude this talk, okay? In conclusion, careful consideration of cryospheric components in GCM can substantially increase subseasonal predictability, I believe. However, notoriously large internal variability over high latitude region, what is that? I don't know. High latitude and less understanding on physics are major obstacles, I think. Far to go to achieve our goal.